So in the last class we have discussed about the Fourier law of heat conduction that relates the four parameters: heat transfer rate, temperature gradient, uh, cross section and the cross section area, and thermal conductivity. So it relates. So Fourier law states the rate of heat conduction per unit area is directly proportional to the temperature gradient. So Q by A, it's the heat flux, is directly proportional to the temperature gradient. And when we remove this proportionality constant, so we introduce thermal conductivity, the parameter introduced for uh, so K is the thermal conductivity. So with the help of these law, we can quantify the heat flux along the direction of heat flow. So in this relation, Q is the rate of heat transfer in kilowatt, heat transfer area in meter square, that is perpendicular to the direction of heat flow, and dt upon dx is the temperature gradient, and the negative sign basically is uh, put on this expression for just uh, making the thermal heat flux as a positive quantity as the temperature decreases in the direction of heat flow. That is why the dt upon dx gradient becomes negative quantity. For making it to positive, we just multiply the negative sign. Now solve this basic numerical problem. The wall of furnace is constructed from 15 centimeter thick fabric having constant thermal conductivity of 1.6 uh, watt per meter Kelvin. The two sides of wall are maintained at two different temperatures, 1400 Kelvin and 1100 Kelvin respectively. And what is the rate of heat loss through the wall, which is 50 centimeter by 3 meter on a site. So how we can calculate this? So first we noted down all the given parameters. So temperature, one side of the temperature wall we have taken T. Suppose we has taken this wall. So the T1 is 1400 Kelvin. This is the T2. Wall of this temperature is 1100 Kelvin. And thermal conductivity of this fabric is given as K, small k, it is 1.6 watt per meter Kelvin. And the length of this thickness of this construction is 15 centimeter, and the cross sectional area of this wall is 15 centimeter into 3 meters. So we just noted down all these parameters. So cross sectional area A will be the same for, and it's 15 centimeter multiplied by 3 meter. Ultimately we will get 0.5. And width, you can say this is the x or length So we need to calculate heat loss through the wall, as the wall is at high temperature at one side and lower temperature at another side. So we just take the so what are the assumptions we have taken for this problem? For finding out the heat loss through the wall, first we have taken steady state. Second assumption we have taken one dimensional heat. Yes, Satish, is PPT visible? Satish?
Yes, sir.
Okay. So one dimensional heat conduction. Through the wall, and another one is the all the property we have taken as a constant. Properties are or constant. So as we apply the Fourier law says it is minus k times a dt by dx. dt by dx is the temperature gradient, so it can find out this gradient by simply T2 minus T1 upon width or thickness of the wall, that is given as 0.15 meter, and this is 1.6, 1.5. T2 is 1100 minus 1400 divided by 1.5. So in this way we can calculate the heat Q as a 4800 watt. Now the another problem based on this, based on the Fourier law of heat conduction. So to determine the thermal conductivity of hydrogen, a hollow tube with a heating wire concentric to tube is often used. Essentially, the gas between the wire and the wall is a hollow cylinder, and this electric current passing through the wire. So these are the method by which conductivity of any gas is measured. So these are the parameter while during the experiment is given, and we need to calculate the thermal conductivity. So wire temperature is 200 degrees Celsius. This is the outer temperature, you can say, and tube wall temperature is 150 degrees Celsius. Current in the wire is flowing as 0.5 ampere, and voltage drop over 3 meter section of the wire is 3.6 voltage. And radius of tube is given as R2 and R1 as 1.125 centimeter and 0.0025 centimeter. Length of the wire is also given 0.3 meter. So when we draw this, and this is the wire, and now how we can find out the heat flux or heat transfer per unit area Q by A is simply minus K dt upon, in this case it becomes dr. So the same assumption we will follow in this case also. The states are heat conduction is steady state, heat conduction in radial direction only, and the properties are constant like thermal conductivity. And so what amount of heat is flown by this electric wire to this tube, we can calculate simply by Q is equal to V into I, voltage into current. 3.6 volt is given, current is 0.5, so ultimately 1.8 watt is given, and this amount of heat we can quantify it readily outward, we are assuming. So readily outward we can find out 2 pi L is the perimeter, and the R1 upon R2 d R upon R, and this is given minus K into temperature, change in temperature from T1 to T2. This simply we are equating this heat uh, heat obtained from this electric resistor wire due to electric current flowing through the wire, and comparing it with the Fourier law. So Q upon A, you just put all these things. Dimension is given. Q upon 2 pi L is constant. 1 by R is ln R. So simply it is ln R2 by R1 1 minus K into T2 minus T1 delta T. And this amount of conductivity you will get Q upon 2 pi into L into T2 minus T1 into ln R2 minus R1. All the parameters given. Q we have already calculated as 1.5, ln 0.125 upon 0.0025 upon 2 pi into 0.3 into delta T is simply 200 minus 150 degrees Celsius. So there is no need to convert this temperature into Kelvin scale, because difference will be the same either in either scale, either Kelvin or degree Celsius. So it is 200 minus 150. This is watt per meter into Kelvin. Now, a second basic law is Newton's law of cooling. You have already studied. It is in your 12th standard. Newton's law of cooling is simply say the rate of heat transfer is directly proportional to the temperature difference between surface and a fluid. So suppose we have taken a flat plate that is placed on the horizontal axis, and fluid is flowing, and this fluid contains heat transfer coefficient H and temperature is T infinity. So this will be the profile of temperature along from top to bottom. So first layer of fluid that is directly contact to the hot plate, it will be the mostly heated. It will be the same temperature as the plate, and gradually it is decreasing the temperature. So rate of heat transfer Q upon A is directly proportional to Ts minus T infinity. And when we put this, the Q, small q is the heat flux, heat transfer per unit area, and this is given H into Ts minus T infinity, or when we take in total heat transfer, so it is H into. So in this equation, H is the heat transfer coefficient, that is the unit of watt per meter square degree Celsius. A is the cross sectional area, T is the surface temperature, and T infinity is the atmospheric temperature. So these are the values of heat transfer coefficient for some fluid like air, water, vaporization of water, condensation of steam. So at atmospheric air, when the free convection is used, so in that case, heat transfer coefficient varies from 6 to 30 watt per meter square Kelvin, and for forced convection, we have taken 10 watt per meter square Kelvin, and free convection, in the case of water, it is ranges varies from 500 to 1000 and so on. So now try to solve some simple numerical problem based on the Newton's second law of cooling and calculate the net heat flow rate. First, you try to solve this. So how we solve this problem? So first, note down the what are the various parameters are given in this problem, like heat transfer from refrigerator valve. So refrigerator valve, when we draw the refrigerator valve, P is given zero point 0.1, T2 is T ambient is given 21 degrees Celsius, H is 10 watt per meter square Kelvin, wall temperature is given. Surface temperature at inside is given as. So what will be the convective heat transfer? So this is the amount. Convective heat flux is calculated with the Q upon A is equal to H times T infinity minus uh, outer surface temperature of wall. So Q is zero point 0.1, point not 1, it is 10 multiplied by 21 minus 16. Now this heat is also conducted through the wall. Therefore, the plane wall, this wall will be, when we apply Q upon A to Fourier law, so it will give K conductivity of wall, outer temperature minus inner temperature upon L. This 50 is equal to. So this will give the inner temperature. So the inner wall temperature is given as the 1 degree Celsius. Another problem is based on this Newton's law of cooling. A hot plate is exposed to an environment at 100 degrees Celsius, and temperature profile of the environment fluid is given as it is depend on the uh, quadratic relation. It depend on the distance also. So thermal conductivity of the plate is given 40 watt per meter Kelvin. Calculate the heat transfer coefficient. So in this case, we need to calculate the value of H. So first try to solve this. So as it is given in this problem, there is a hot plate, and the thickness of this plate is given as dy, and surface temperature Ts is Q convection. So we need to find out the heat transfer coefficient. So first of all, we assume the steady state condition and then apply the energy balance on this plate. So whatever the heat conduction to the plate from top to bottom, this is equal to the heat convection. So Q, now apply the Newton's law of cooling and Fourier law of conduction for calculating the heat transfer coefficient in this problem. So when we put this relation, Q conduction is minus Ka del T upon del Y at Y is equal to 0, and this is equal to HITS minus T infinity. So here, what is the temperature of the plate at the 60 degrees Celsius? So Ts is the temperature of the so Ts is given as the expression 60 plus 40y plus 0.1 by square. And when y is equal to so surface temperature we calculated at y is equal to 0. By this expression it is Ts equal to 60 degree, and when we putting y, we will get the value of now del T upon del y. We get differentiate this equation. So dt upon del y, so 40 plus 0.1 into 2y, and at y is equal to 0 again you will get the 40 degree Celsius at y is equal to 0. So using these value dt upon dy at y is equal to 0, you will get, just compare, minus 40, this is the thermal conductivity, into 40 degrees Celsius, that is the 40 degrees Celsius per meter. This is the gradient, temperature gradient, and minus 40 watt per meter Kelvin. And when we equate this with heat transfer due to convection, so H into 60 degree minus 100 degree, and in this way we can find out the value of H as the 40 watt per meter square into Kelvin. So this is the overall heat transfer coefficient. So we will stop the session here. So or we can also discuss some Newton's. It, I have 10 minutes more, so no problem. We just carry forward this. So another basic law of that is frequently used in the heat transfer analysis, that is Stephen-Boltzmann law of thermal radiation. So this law, as you have already studied it in 12th, so briefly we just explain this. So it states the rate of heat transfer per unit area from a black surface or black body is directly proportional to the fourth power of the absolute temperature of the surface. So QIA is directly proportional to the surface fourth power of the surface temperature. And when we remove this proportionality constant, sigma is placed, that is also called Stephen-Boltzmann constant, that has the value of 5.67 into 10 to power minus 8 watt per meter square Kelvin raised to power 4. So when we taken the real surface, not a black surface, then heat flux emitted by real surface is always less than the heat uh, emitted by the black surface. So for that case, we used some Q upon A, that is sigma. We just introduced the emissivity. Emissivity, that is the effectiveness, you can say, a radiative property of the surface. So for the when we deal with the real surface, we just use this parameter where epsilon is the emissivity. Now, what will be the net radiation heat exchange between the real surface and its surrounding? So this amount of heat is radiated by the real surface, and so and the surrounding temperature that has the T infinity. So we will quantify the amount of heat Q upon A sigma epsilon Ts raised to power 4 minus T infinity raised to power 4. So where T infinity is the surrounding temperature, temperature in Kelvin, Ts is the surface temperature. There are some other laws related to the radiation that are Planck's law, Wien's displacement law, and Kirchhoff law, which is also used while analyzing the problem in radiative heat transfer. We will discuss in detail in the last module, that is specifically designated to the radiation. And now combined convective and radiative heat transfer. So combined convective and radiative heat transfer. Sometimes in many of the engineering applications, we can see like a boiler, when the surface temperature is much higher and the heat transfer from surface may be taken place simultaneously by the convection and radiation to the surrounding. So for that case, we can model uh, by considering both radiation and convection, and that is called as the combined convective and radiative heat transfer. Suppose this is the surface temperature and it is very high temperature, so heat is transferred in two way. One is the convective and other one is the radiative. So this is the radiative convective resistance and the radiative resistance. T infinity is the surrounding temperature. So when we consider a surface emissivity epsilon, and that is maintained at a temperature Ts, so exchange of energy by convection and radiation with the surrounding at temperature T infinity or surrounding temperature, we can quantify the loss as the sum of these two, convection and radiation. So this is the convective heat transfer coefficient, A is the cross section area, and Ts minus T infinity plus radiation sigma epsilon A Ts raised to power 4 minus T infinity raised to power 4. So and suppose we just introduce a surface heat transfer coefficient, surface heat transfer radiation or radiative surface heat transfer coefficient HR. So in very convective heat transfer in similar fashion as a convective heat transfer, we can uh, take this heat transfer as a HR into A into Ts minus T infinity, and equate this HR with the radiative heat transfer coefficient, that is equal to the sigma sigma epsilon A Ts raised to power minus T infinity raised to power 4. So we can find out this radiative surface heat transfer coefficient, which we are assuming. So in that case, its value comes epsilon 0 Ts upon uh, just so if surrounding temperature is much less than the surface temperature, so we can linearize this relation HR as the sigma epsilon Ts square minus Ts in T infinity square into Ts plus T infinity, and this HR, if taken this condition, so it becomes sigma epsilon Ts raised to power 3. And when we replace this HR in place of the radiation heat transfer coefficient, using this radiation heat transfer coefficient in particular in first equation, this one, so we will get Q as HCAT S minus T infinity plus HRATS minus T infinity, and this is HC plus HRA into Ts minus T infinity. So the convection and radiation heat transfer coefficient Hc and Hr comes into this. So we can calculate with the help of these relation as the combined in case of combined convective and radiative heat transfer. So now so we just stop the session here, and we will discuss further in the next class. Satish, Indrajit.
Yes, sir.
Acha. So have you? I see in your class you have there is 2 3 class earlier held by some other faculty member.
Yes, sir.
So what content uh, he covered till date?
Uh, जी सर.
What content कितना उन्होंने कंप्लीट किया है अभी इसमें फर्स्ट मॉड्यूल में?
अदर सब मतलब सर वन यूनिट करीब कंप्लीट हो गया, बट हम लोग बाद में ज्वाइन किए, पहले पता नहीं चल पा रहा था.
Actually, this is my first class.
Okay, okay. Okay, Indrajit, this is your first class.
Yes, yes, sir.
Okay.
सर माय फर्स्ट क्लास.
अच्छा, Satish. Okay.
Yes.
So no problem. I just started by today, and we are just taking from started from the basics. So first, briefly explain in first class. You will check it from the recording. What are the various important parameters? What are the various uh, terminology used in the heat transfer? And then what are the various important laws that is frequently used in this course? So we are starting from that, and tomorrow or next weekend, next class, we will discuss some thermal conductivity. So and then start basic conduction equation. So there will be no problem to all the newly admitted students. You can you will grasp easily. Okay. Actually,
Yes, sir.
heat transfer problem is a little bit more. It involves much mathematics or some equation, differential equation, and something. So sometimes it becomes very cumbersome. Okay. कंडक्शन तक तो ठीक है, when कन्वेक्शन आता है तो उसमें भी आपका बहुत ज़्यादा इन्वॉल्वमेंट हो जाता है उस टाइम फिर के रिलेशंस का.
सर हीट ट्रांसफर की और भी क्लासेस हो चुकी हैं, अभी फर्स्ट क्लास है आज.
मैं आज फर्स्ट ही क्लास लिया हूँ, सेकंड क्लास है, इवन एक उसमें थी आपकी फर्स्ट हाफ में 1 to 12 to 1 थी एक क्लास, और ये अभी है 3:15 to 4:15.
यस.
तो पहले ही है, इसके पहले कोई और फैकल्टी 1 2 क्लास ही लिया है, उन्होंने भी ज़्यादा नहीं लिया था.
इसी में सर सेम सब्जेक्ट में सर.
सेम सब्जेक्ट अब पता नहीं मुझे, उस पे टीम पे देखा था मैंने.
बट the problem is due to university
Okay.
not provided my email ID, university email ID and password.
Okay, I also got it is later actually.
Yes.
Email ID and password.
Actually, I have your personal email ID. I'm just telling you, just wait. We take Satish, your email ID is satish12101987@gmail.com.
Yes, sir. Yes, sir. Correct.
Indrajit, your email ID, I don't have your email ID. So
Yes, yes.
so if you just text me your email ID, so I will include your name here also.
Yes, 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 sir. I just share in the group.
Okay, just
Group or classroom, maybe class.
no, you can just text in this team, no? Just message me your email ID.
Okay.
I will note it down, so that when we schedule next class, so you will get notified, and check your spam folder also, huh? Because generally mail is given to the just floating on this spam folder.
Yes, sir. I checked.
I have sent my email ID.
Okay, okay. I just noted down. Indrajit, yes. So no problem. In next time we will. इंद्रजीत, आप अपना स्पैम में देखना, आपका ना शायद इंद्रजीत
Yes, sir.
इंद्रजीत.मंगलायतन@gmail.com.
Yes, yes. This is from university. Another mail ID from university, that is 20. That is my
Okay, okay, no problem. I noted down your both of your
yeah,
email
yeah.
ID.
This is my actually personal mail ID.
Okay, okay, okay. No, no, no problem. Okay,
Actually 2021.202151 dot मंगलायतन @edu जो है इसमें.
edu
okay,
dot फिल करते हैं.
Yes, yes, yes. Actually, I got all the information from this 2021 50 30 31.
okay.
2021 50 31 underscore Indrajit @mangalayathan dot edu dot in.
Okay. 20. So I just noted your indrajit.sarkar.ma@gmail.com, and other one is
Indrajit Mangalayathan. Yes,
indrajit.mangalayathan@gmail.com.
yes, 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 yes.
So no, no problem. I will mail you all of you.
Okay,
Yes,
The
okay.
next class will be Saturday. Okay. Saturday.
sir. Evening.
Maybe I will talk to your concerned PL or program leader, so
Yes,
that
sir.
actually two class a day it's be heavy, na, for both of you, student and faculty.
Yes,
सर
sir.
So
सर
yes.
आप स्टार्टिंग से चला सकते हैं जैसे शुरू से.
हाँ हाँ, शुरू से ही है, ये शुरू से ही है.
अच्छा, जो पहले हो चुका उसको छोड़ के ना सर.
हाँ हाँ, कोई प्रॉब्लम.
यस सर. ठीक है सर.
Okay, sir. Thank you.
ओके ओके ओके.
Thank you.
ओके सर.
थैंक यू फॉर अटेंडिंग क्लास.
थैंक यू सर.